And we're back. So this is question 4 out of the review, out of the 4.9 and 5.1 review. Again, I just got done saying that you want to, if you would like to, you can take the derivative, whatever you end with, it should get you back to your original function. I use capital F for this, for the antiderivative. Okay. Now, you got to think about what will get you back to sine. Right? What will get you back to sine? What is the antiderivative of sine? And I'm trying to get back to positive sine, right? See, if you just accidentally wrote this, like maybe you just said, oh, sine is cosine, right? Cosine x, or cosine theta. Oh, I should have done x. Oh, that's kind of weird. Should have been x.
Right.
Yeah. Look, I did 2 different variables. Oh, that's odd. Okay. Yeah, the book did that. Yeah, I didn't do that. Yeah. You know, it's not even there. Whatever. So if you had mistakenly just said 4 cosine x, and then minus 3, kick up the power 1, divide by that number, plus a constant, and then you said, okay, if I want to find the derivative of that, what's the derivative of cosine? Negative sine. So that would have gotten you to negative 4 sine x. And then you could find the derivative of this and get you back to negative 3, right? So to kind of correct that, I would have needed to take 4 times, and I'll write it like this for the first step here, negative cosine x, right? That, the derivative of negative cosine x will get you back to positive sine x. That's why f of x is going to be negative 4 cosine x minus 3 over 2 x squared plus a constant. Remember, put the plus a constant on the end of any one that I asked you for the general antiderivative. Question about this one?
Yeah. Can I keep it as 3x squared over 2, or do you always want me to pull it out?
Either way is fine. Any other question about this one? Go for it. On the review? Okay. Okay, a particle is moving with the given data. Find the position of the particle. Now remember the position, the derivative of the acceleration is the velocity. The derivative of the velocity is the, I'm sorry, I'm saying that the other way around. Antiderivative. The antiderivative of the acceleration is velocity. The antiderivative of velocity is position, right? So what I can say here is that if I want to find the antiderivative of acceleration, that's going to be velocity. So we find the antiderivative, we kick up the power 1, 7t squared over 2 plus, just add on the t, plus a constant. Now, I give you some information. I say v of 0 is 6. I didn't necessarily need to give you v of 0, did I? I was just very nice to you when I gave you v of 0. I could have given you any one ordered pair, and you could find your c value just by plugging in your t and seeing what you get out. Just by plugging in the x and y, finding that last constant. But I was nice to you. See, this means that that value is 6. So my velocity equation is 7 over 2 t squared plus 2t plus 6. Everybody follow me to that? And then I do the exact same thing again. I find the antiderivative of that to find the position. Because remember, the antiderivative of velocity is position. Oh, I think I did it. I made it as 3.5 on the key. It's fine if you leave it as fraction format. So now position is the antiderivative. So s of t is going to be equal to, I didn't make it s, right? Yeah, s of t is equal to, and then we can have 7 over 2 t to the third, all divided by 3, plus 2t squared divided by 2, plus 6t plus my constant for position. but I know my constant for position because S of 0 is 2. So now let's just manipulate that a little. Let's just simplify that a little bit down. 7 halves divided by 3 is times 1/3. So 7/6. 7/6. So S of t, you could have also given it to me as a decimal. 7/6 t to the 3rd plus t squared plus 6t plus my constant, which we know is 2. That's the position function.
When the velocity of the 0 is the velocity of the 1.
Yes.
So you just plug those into t and then we just solve for.
Yeah, let's do that. Let's say I had this function and I had said instead of velocity of 0 equals 6, I said velocity of 1 equals 6, right? So what would that make our constant? What if I had changed this and I had said, okay, instead of v of 0, what if I had said v of 1 is 6? Well, then that would make this here v of 1, which is 6, is equal to 7 halves times 1 squared plus 2 times 1 plus c. And then you can just solve for c. Does that make sense? So 7 halves plus 2, subtract it over, and that would be your constant. Does that make sense? Yeah, and then you just keep going from there. You find your number that's a constant, and then you keep going, do it to position, do it for position, and then you have your S of 0. And again, I didn't need to give you S of 0 here. I could have given you S of 2, S of 3, whatever. You still do that same process where you can plug in whatever inside the parentheses, and then get out what you give me. Yep.
On number 5, in the final step, you had x plus 1. It was the one where you get f double prime and you have to go all the way to f.
What did I do wrong?
I don't know if anything's wrong. I don't know how you got that.
That is a C. Oh, why did I do a parentheses? That is a CX plus D. That's not an X plus 1. That is a CX plus D. Yeah, that does kind of look like an X plus 1 inside of X. Yeah.
Does it matter what order you do it in? So do you have to do the v equation then the x one?
Yes,
Okay.
you have to, because the antiderivative acceleration is velocity. It's got to chain together. It's going from acceleration to velocity to position. Yeah.
So in number 5, is it just the same process, like find the antiderivative twice? And that'll be it?
Yeah. And then you're going to have 2 different variables for your constant. That's why I said plus CX plus D. For him. You can make it whatever you want. I'm just going to use D.
We'll go over some.
Yeah. Okay, so we're going to use right side approximation and left side approximation to find kind of like a boundary between for the total area, for the exact area. All right, so let's do right side approximation first. I don't know why. Let's graph it. Now to graph it, I'm going to go from 1 to 3 of square root of x. So what's the square root of 1? 1, right? And then, so here. And then what's the square root of 3? Well, it's just a little less than 2, right? Because the square root of 4, 1, 2, 3, 4, would be 2, correct? So I know this is generally going to go out to here. So if I was, sure. So maybe it's going to be around right there, right? I could get the decimal form of it, and I guess why not? What is the square root of 3? 1.73. So I estimated it pretty good. 1.73. All right. So that, I want to find the area under the curve. Okay, I want to find the area under the curve. So what I'm getting at here is I want to find this area. That's the area that I'm looking for. Find that area. Now to do this, I'm going to use, why are you doing that? I'm going to do this. Thank you. To do that, I'm going to use left side approximation, right side approximation. What did I say I'm going to use? Right or left? Uh-oh. least he's right.
I can get rid if you don't want to.
I'll do that. It tells me you right. How you digress. All right, so here, this is 1, this is 2, this is 3. So that makes this 1.5 and 2.5. How many rectangles did I say? 4. Okay, 4. Which makes sense. I'm going to cut it into halves here. I'm going from 1 to 3. And I could find that exactly. You know, delta x is always going to be equal to b minus a over n, right? b minus a over n, which is 3 minus 1 over 4. 3 minus 1 over 4. So it's 2 over 4 or 0.5, which makes sense. Look at my intervals in here that I'm going to make. 0.5, 0.5, 0.5, 0.5. Gregor.
What did you do to find the slope of that curve?
I just estimated by plotting points.
So it could be like anything.
Right. Like in the original problem that we did in the notes, I did x squared. In the homework, I think it was like 1 over x. So you could just plot it using like 1 and whatever your endpoints are, really. Yeah.
So it doesn't matter how tall it is.
Right. I mean, just looking for an estimate of what it looks like. Because in the end, I'm not going to use the graph to estimate the area of these rectangles. I'm going to use the actual numbers.
Well, if you were to do a negative sloping curve, would it matter for being different?
No, just know that then the other side approximation, like this one, when I do the right side approximation, it's going to be an overestimate, and the left side is going to be an underestimate. If it would be negative sloping, it would flip that between in terms of over and underestimate. All right, so now let's create our little rectangles in here. Let's use right side approximation here, 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 and here. Now, how am I creating those? I'm making sure that each rectangle, the right side, top right side is going to be on the graph. Let me shut the door. The top right side is going to be on the graph. That's what I mean by right side approximation. Now, if I were to use left side approximation, then the top left would be on it, and you'll see that in a second. So let's find the area here. The area is equal to, and I like to do it this way. I like to put my delta x out front and then write the sum of all the y values. The sum of all the y values. Now, this is right side approximation. I'll use this notation, R4. Right side with 4 rectangles. All right, so now I want to find f of, do I want to use f of 1? No, because f of 1 is not the height of that rectangle. F of 1.5 is the height of that first rectangle. So it's the square root of 1.5 plus the square root of 2 plus the square root of 2.5 plus the square root of 3. Could I have distributed that 0.5? Of course. But you're going to see, I'd like us to try to start pulling out that delta x, because that's going to help us when we write our sums in the end when we start looking at integrals. All right, so now let's estimate it. Let's say, okay, we've got 0.5 times the square root of 1.5 plus, and your parentheses, plus the square root of 2 plus the square root of 2.5 plus the square root of 3. One more parentheses. Yeah. 1/2 times each of those values, each of the y values. How did I get the square roots? All I'm doing is taking the x values and plugging them into the function. That's all I'm doing there. 2.976. Let me just make sure my estimate came out to be the same. Yep, 2.976. So R4 is 2.976. Over or underestimate? Overestimate. Now, we do the exact same thing, but we use left side approximation. I'm going to do the exact same intervals and everything. So point here, 1.7, I think we estimated the square root of 3 to be. So here, and now we're going to use left side approximation, which means that now I take the point on the left here, and then the point on the left at 1.5, and then the point on the left at 2, at 1.5. Am I using, whoop, am I using the f of 2? I'm sorry, f of 3. Am I using f of 3? No, I don't use that last point. Okay, that height right here, that value is not one of the heights of the rectangle. So I say L4 is my difference times the y values of each of my heights. The square root of 1 plus the square root of 1.5 plus the square root of 2 plus the square root of 2.5. And again, I'm not using the square root of 3. So really, I always do this. I just go back in and I just change, like the 1.5 is there, the 2 is there, the 2.5 is there. I just need to go back in and change this guy here to square root of 1. Because I don't want the square root of 3, I want the lower boundary, the square root of 1. 2.61. 2.61. L4 is 2.61, which is an underestimate. So I know the true area underneath the curve is somewhere between 2.61 and 2.98.
Would it matter if we rounded the right side?
To the 100? Yeah, that's fine. Yeah. Pretty soon, we're not going to even need to estimate. We're going to be able to know. So I think we'll be all right.
Would you tell us if we do the one?
Yeah, I'll tell you if you do that one.
So you're gonna tell us how many you want to see.
Yep, I'll tell you how many rectangles I want, and I'll tell you whether I want left side, right side, or middle.
Okay, I was confused because on like the homework one, you said we're doing the y values.
Yes,
And then didn't you put the x values in the?
I'm putting the x values into the function. The function is the square root of x, right? So I'm putting the x values into x. Okay. This is technically, like that square root of 1 is this coordinate. 1 comma the square root of 1, right? And that coordinate in there is 1.5 comma the square root of 1.5. So all I'm doing is taking the base of this rectangle times its height, which is the y value here. That's why I'm adding in the square root of 1.5. Yeah,
If it's different than you might do.
exactly. That's why in the homeworks it was that 1 over x. It was 1 over 1. This would have been 1 over 1.5 or something like that. Does that make sense? Yeah. That's why in the notes we were looking at just y is equal to x squared. So that's why it was just those x values being squared within the parentheses. Yeah.
For the middle, so when you find it, you want to do the 1.35.
Yeah. If I wanted to do middle approximation, let me just show that. Okay. So I'm going to do the exact same thing here. Graph it out. Oh, okay. Let's graph it out. Let's use 1 comma 1, 2, 3. Here to something like this. Okay, there we go. So I would want to use, so there are my intermediate values, yeah? I would want to use these heights. Okay, so here's my middle point. That's the middle of my rectangle. Right? Right there.
Would it still be 0.5?
No, it would change it.
Okay.
Oh, I'm sorry, the interval?
Yeah, like on the outside of the fence.
That would still be 0.5. I'm sorry, I cut you off too soon. That would still be 0.5. Okay? M4 would be 0.5 times, but what would change is what's inside the parentheses. Because the height of the rectangle is now the midpoint in there. Like here, this is 1, 1.5, 2, 2.5, and then 3. What's the true height of that rectangle? F of what? 1.25, right? F of 1.25, because it's directly in the middle between 1 and 1.5. So that would be the square root of 1.25 plus the square root of, now what's my coordinate here? It's halfway between 1.5 and 1.2, 1.75. That's a point there. Plus halfway between 2 and 2.5, 2 1/4, plus halfway between 2.5 and 3, 2.7, or sorry, that's a 2.25, this is 2.75. Sorry for my poor handwriting. Okay, and then we would just plug that in. Does that make sense? That's how we would do middle approximation if I asked you to do that. Do we know whether middle is an under or over? No. Okay. Any other questions? What other questions do we have on the review or any of the homeworks? What's that? We just saying 8. 8. Oh, 8. 8. Oh, I thought you were just saying hi. Hey. Hey. Hey.
Have you seen that video of the girl who
All right. Speed of a runner increased steadily during the first 3 seconds of race. Speed of half-second intervals is the given data in the table. Find the lower and upper estimates for the distance she traveled during these 3 seconds. I don't even know if this is like accurate. Hush was like plugging in numbers. I guess I should check with a runner.
I'm that fast. Or is that slow?
I don't know. See, that's what I don't know.
Aren't you a runner?
Me? I don't. Yeah, but I don't like have like my velocity in feet per second.
Only real runners do that.
Apparently, that's why I'm not a real runner. The speed of a runner increased steadily. So I want to know what the lower estimate and what the underestimate, or the underestimate and the overestimate is, right? Now, what is my delta x in this case? 1/2. Did you see how the time intervals are changing by a factor of 1/2? I could have also seen that by taking 3 minus 0 divided by 1, 2, 3, 4, 5, 6. 1/2. Okay, because I would have 6, whether I do the right side or left side approximation, I would have 6 approximations going on. So, but I didn't need to calculate that because I could see it plain as day in the table. I got to have regular intervals there. So I know I'm going to use my underestimate is my delta x, or 0.5, times the y values. See, the reason why I write it like this is because now my y values are just going to be what's inside my parentheses here. Just like the calculation for right side and left side approximation using rectangles. Same thing here. 0, 6.7, 9.9, 12.2, 13.6, and 14.7. That's my under. My over, 0.5, and now I exclude the 0, but include the 15. 6.7, 9.9, 12.2, 13.6, 14.7, and then add in the 15 and 15.3. Let's run those numbers there. That gives me a 0.5 quantity, 6.2, oh, that's a 7, 6.7, plus 9.9, plus 12.2, plus 13.6, 14.7. And I end it there. That's my underestimate, 28.55. Ooh, 2.855. 28.55 feet. My overestimate, I'm going to do the exact same calculation, but now I'm going to add in 15.3, which that gives me 36.2. Questions about that one? That's all it is.
If the first number was like 0.17, did
Yeah.
you just know that was the overestimate then?
No, that would be,
Because then the number that you were adding was bigger than the last number.
yeah. No, that I think this is only working from like, if you're starting from zero.
It's different.
I guess if we had not started at zero velocity, you're right, you wouldn't really understand whether it would be an over or under, whether I'm decelerating or accelerating. I know because this is I'm increasing, I know that as time goes on, I'm increasing, that the left side approximation being under would be starting at lower values.
Another one was like probably the large one was more random.
More random, yeah. Yeah. And that was because This one is an under because I know that I am increasing. If I know that I am increasing, then if I start at any given value go up, whatever I calculate is going to be an underestimate, rather than if I start at the end and you put the first number, that's the over. Because I know I'm increasing steadily. Is that valid? Like traveling 30 feet in 10 seconds?
Yes, I do.
I mean, as a runner?
Oh.
I think so.
Go travel 30 feet right now. Okay.
Yeah. What time you?
For the same question that Amanda's having,
2.
for like if the Y values are random, do you need to write them out in order then?
No, it doesn't matter, because you're adding them. It's no big deal.
Okay.
Yeah.
So like if like the biggest number is actually like the second one?
Yeah, you don't want to worry about reordering them because this is the half-second interval time. Like, this is time, this is what the velocity is at these given time intervals.
Okay.
You know what I
So you
mean?
won't know which one's over and under until you do it then?
Well, I know because I know
Not
I'm
for this one, like,
increasing steadily.
If they were random?
Right, or if I had not told you that I was increasing, you wouldn't necessarily know whether it's an over or under. Yeah.
Thank you.
Okay.
We're in a couch now. Is that video?
Yeah, everything's recording you.
Oh, I thought you had a
No,
video.
there's no video evidence for me.
Yeah.
Like I said, oh no. And that's the crazy thing, like I didn't live in the day and age where everything was recorded. All the stupid stuff I did, nobody recorded. Not that I did anything. No. 21 on which homework?
Navy.
The 5-1, yeah.
Coronado, California. I should predicted the pandemic. They released this virus in California. Yes. On stage. They injected it in a bat and they sent it back.
21? Is that what it is? Okay. It's not on the review, so I think you're right. But let's go through it because it's good to talk about. We can ignore it, like it doesn't even exist. So I know my function is 2x over x squared plus 1, and I know I'm going from 1 to 3. I mean, this is going to help us. Understanding this stuff is going to greatly help. It's going to help us immensely when we get to integrals, because we're going to need to calculate things like this. Okay? And how does this relate to antiderivatives? Basically, what we're going to be learning in the next section, a little foreshadowing here, is that if I'm able to take the antiderivative from one to the next, I can actually find f of the antiderivative, and that'll give us the area underneath the curve, which is kind of convenient. No more estimation, we would know exactly. So use, I know I want to find delta x. Oh, that's the wrong side. Delta x is b minus a over n. So 3 minus 1 over n is going to be 2 over n. That's our delta x. And remember that the formula is limit as n goes to infinity of, and I'm just copying here, delta x times the sum of, from I goes to 1 to n, f of a plus delta xi, which is essentially what you do when you find left side and right side approximation, right? That's essentially what you do when you find left side and right side approximation. You just leave off this limit because you know exactly what it's going to go to. You say, okay, I'm going to use 4. Well, you take your delta x, which is your change in your x, right? Your base of each rectangle, times the sum of all of the y values, f of these things plugged in. And we're able to tell exactly what those things are. When I graph it out, like from 1 to 3 using the square root of x, I can actually figure out what those x coordinates are and just plug them in. What those x coordinates are, really your starting value plus delta x, your change in x, times I, which is the number of strip that you're taking. So let's figure this out. Well then, a plus delta, I want to plug this in. We know that a is 2. Right, so this is 2 plus delta x, which is 2 over n, times I.
I thought
Oh, 1, ooh, sorry, A is 1. Scared me there. I saw this 2, and I just went for it. So A is 1, so this, I'm plugging in 1 plus delta x over I, 1 plus 2 over n times I. So that gets me a limit as n goes to infinity of delta x 2 over n times the sum of, as goes, the sum of I going to 1 to n goes to infinity, of f of 1 plus 2 over n times I. So plugging that into the function, that would be 2 times 1 plus 2 over n I, all divided by x squared, 1 plus 2 over n I squared, plus 1. And for right now, we leave it like that. We're going to figure out how we evaluate that eventually. But not yet. Yeah.
So, now we're just, so they basically finding delta x, because you plug the 1 in for A.
The only way we use 3, the only time we use 3 is finding delta x. Yeah. The starting value is the more important piece there. Any other questions? For the good of the order?
I'm good.
Okay, let me stop the video then.
Bye.